All right, the next presenter today is going to talk about oneAPI, oneCCL, and OFI. Sayantan Sur is a speaker and he's a principal engineer at Intel. He's an expert in MPI, fabrics, and HPC. He's currently focusing on a oneAPI stack for Intel GPUs. Sayantan is well known in our fabrics community for his work in scaling MPI over InfiniBand. His work enabled MPI to scale from new InfiniBand connected nodes to thousands. He has published more than 30 papers and has delivered several tutorials at conferences such as Supercomputing, Hot Interconnects, and our very own OFA. Sayantan received his Ph.D. from Ohio State University. And then you should be able to speak, and let's see if we can hear it.
Hey, thank you, Divya. Can you guys hear me?
Yes, we can. Thank you.
All right. Thanks for the introduction, and thanks for the mention from Dr. Panda. I've worked with him for many years, and been engaged with this community. So it's just great to come back here and talk about oneCCL. Can we go to the next introduction slide? Okay, so as we have seen, I think some of the fonts are kind of messed up. I don't know, Divya, is that something is going to happen in all the slides, or?
Let me check. You keep going. I'll verify in the back end and try.
Sure. So as we've seen, like the workloads are getting kind of specialized, and the application workloads are requiring diverse hardware. Some latency sensitive workloads require scalar processors, and like denser compute requires vector and matrix, and pipeline execution requires spatial processors. So as we've seen that these demands have increased, there have no common language or APIs that have emerged to actually support these applications in a cohesive manner. As a result, what is happening is that every type of application that actually targets a different type of architecture has to perform, kind of jump through a lot of hoops to port to a certain architecture. Their tools don't work across architectures. Their programming languages don't work across architectures. And worse, if you have a single application that can actually combine many of these needs, then it becomes kind of a nightmare. So that's really where like oneAPI was born, and it offers a unified and simplified language. We call this data parallel C++ and OpenMP and others. It's like focusing on enabling the applications to express their parallelism, and it is all the components of oneAPI are based on industry standards and open specifications. But out of this oneAPI, there's also one industry initiative, and that's also part of it is Intel product. So those two things are separate. And oneAPI is interoperable with existing HPC programming models. So many of the components are actually quite familiar to the HPC ecosystem. Can we go on to the next slide, Divya? Okay, so let's jump into deep learning, and Dr. Panda mentioned this also before, and I think there have been several talks on deep learning at this workshop before. So as we all know, deep learning is just a branch of artificial intelligence where you're trying to train a neural network using either labeled or unlabeled data, and it's a very compute-intensive task, and there's a lot of data involved. So as a result, to speed up this training process, we like to distribute the computation. You either replicate the neural network model itself, or you keep the model the same and then feed different instances of the model, different data sets in parallel. So essentially what ends up happening is that you're introducing the need for communication in the training process. And the communication is a collective nature, and Generally, collective routines like all reduce, reduce scatter, all gather, reduce broadcast, and all to all are used. So as part of the oneAPI initiative, so this oneCCL is our oneAPI collective communications library that aims to expose these fundamental primitives up to the deep learning frameworks in an application-friendly pattern. And I saw that Mikhail Sharayev, who is one of our architects of oneCCL, is also online, so it's great to have him. You know, as I mentioned, oneAPI is an open specification. So I've put the link for the open specification for oneCCL. And also we have open source implementation, which is up on GitHub. Folks are encouraged to go check that out. Data, next slide. Okay, so let's jump into the oneCCL you know, architecture and the features. Next slide. Okay, so oneCCL is built on top of common scale-out APIs such as MPI and libfabric, which should be quite familiar to this crowd. So MPI and OpenFabric's interface, OFI or libfabric, they are providing a lot of portable abstractions, and many vendor hardware is actually supported under both of them. So one of the parts of the oneAPI stack is this level 0 interface, which is providing basically low-level direct-to-metal interface for devices in a oneAPI platform. Typically, right now it is used for communications within the node, say between a bunch of you know, GPUs, FPGAs, and so on. And oneCCL provides an abstraction that is friendly to the you know, frameworks and the libraries, but can internally encompass all of these various backends. So based on the you know, like the platform needs or the application needs, different backends can be chosen. Next slide, David. Okay, so the oneCCL programming model really consists of a stream, which encapsulates execution context, and streams provide the application's execution context, really, and provide the sort of ordering of the collectives and so on. So every stream represents an independent a series of independent ordered set of operations, and it also includes a communicator construct, which defines a group of the participants in the collective operation, and here the rank can either be a CPU or a GPU, and you know, like generally when you launch the job, you get the rank from the host, and you assume that if you have a GPU connected node, then you assume that the GPU is part of that rank. And then of course we have the collective operation itself, which is you know, like the operation that is being executed by the set of ranks. Can we go to the next slide? So as an example of what we mean by you know, application-specific collective APIs, there was recently some you know, research which showed that some language models which have very big embedding tables like to do or reduce within you know, subtensors inside this large table. So if you look at the traditional all reduce API, that will have input buffer and an output buffer. If you try to use that traditional API, then essentially what the application has to do is extract the extract the portion it wants to reduce from within that large embedding table, and then do the reduction and then copy it back. So not only does it impose a productivity burden, it can it can also represent a performance bottleneck, because now you have multiple copies involved, and if these sensors are big, then there's a memory overhead. On the other hand, if you just call reduction on the whole thing, it's too much performance loss. So one of the APIs that our team came up with is to have the sparse all reduce operation, which essentially lets the application very flexibly provide a starting range of input indices and a starting range of where the receive indices also begin. I've just shown the API over here. There's a lot of parameters. I don't intend to go through that, but if you are interested, if you go to the link before in a couple of slides before, that will describe all of this stuff in detail. Can we go to the next slide? Another productivity feature we found was that some frameworks have a local scheduling approach with the compute graph that has been offered to the device, either the CPU or the GPU, and based on its local execution, certain set of tensors will become ready for doing the all reduce, and over here, typical APIs such as MPI will require in-order calls of the reduce operations on all the processes. But the framework is not really producing the output in the same order. So typically, what has to happen is like some other kind of middleware, say like Harvard or some part of the framework itself, has to reorder these calls so that when you actually do call the all reduce operation, everybody's calling the same all reduce. So in this picture, I'm showing that say like rank 0 is ready to do all reduce A, but rank the other ranks are actually trying to do the all reduce for the tensor B. So when the rank 0 broadcasts its intention to do the A, the other ranks realize that my reduction is not going to take precedence here. So they postpone the B, and then they are able to execute A. And then finally, when rank 0 is able to broadcast B, they can then execute B. This allows basically a better impedance matching from the deep learning framework to the collective layer. And in this picture, I've just shown a conceptual diagram of like how the scheduling can be done, but it doesn't represent an optimal scheduling. So obviously, an implementation of oneCCL can perform any amount of platform or system-specific scheduling using like a whole host of variety of algorithms that can be conjured up. So, but the key thing is that if you abstract this requirement from the framework into oneCCL or any kind of collective library, then we have the flexibility of adapting that without changing any upper level middleware or software like that. Next slide. Another example is this prioritization of collectives. So we've seen that in the typical data parallel training operations, different layers of the training can actually have different priorities. Like the last in, first out model seems to be what is close to what the applications desire. But also we have this hybrid situation where you could have a collective in the model parallel portion of the the training, where that is basically a blocking collective, and any number of mix of things can actually happen. So as a result, what we thought that we, instead of trying to guess what the priority is, or to have a very static scheduling of these collectives, why don't we expose this priority up to the application so they can set basically what priority they want, because the application or the framework here is actually aware of the entire order of things that is actually going on. So you can submit a collective attribute property and for every individual collective. Can we go to the next slide? Okay, so another sort of a detail is that, and the MPI folks probably know this very well, is that the collective initialization can be costly because you have all these different buffers at different nodes. If you're doing zero copy and you're doing RDMA, then you need to have this buffer registered. You may have rendezvous handshakes to get the remote keys and so on. And then finally, the cost of creating the tree itself. So again, instead of trying to guess which collective topologies may be reused many times, oneCCL exposes this parameter that allows an application to specify which collective will be reused. So if you set this attribute to cache equal ones, then it makes sure that the information passed in that collective is actually stored for subsequent use. In contrast, standard APIs like MPI expose persistent things that you have to basically create separate collective requests, and then once you create that, you can't really change any of the parameters. So this basically is a much more flexible, and it stores by the match ID that was specified in that collective. Can we go to the next one? Okay, so in the last 10 minutes or about 5 minutes, I wanted to take an example of like how oneCCL is being used. And this is a recent paper that was written by folks at Intel, and one of the authors, Mikhail, is actually online. Can we go to the next slide? So in this paper, what we were looking at is we are looking at these deep learning recommendation models, which are starting to come out, and Facebook has released this DLRM benchmark. These are just basically your multi-layer perceptrons and have a lot of embedding table lookups, and these are used for essentially recommending products to folks, and there's a lot of lookups and a lot of communication. And the unique thing is that it's unlike other benchmarks and other topologies, it's actually stressing all the aspects at the same time. Like it is stressing the compute capabilities, like in the MLP portion has a lot of gems. And then the network bandwidth is being stressed by an all-to-all operation, which is the order n square communication, and the memory capacity is being stressed by the size of the embedding. Now, tables themselves, and then the memory bandwidth is being stressed by the embedding table lookups. So this is really marking like a new beginning for these deep learning workloads. Can we go to the next slide? So focusing on the communication aspects themselves. So we have the all-reduced operation, which is used for your standard data parallel part of the training operation, where the weight gradients are being averaged. And this is for the MLPs. And as folks are probably aware, we need to ensure overlap with the gem to get good performance. In this implementation that was presented in the paper, we can overlap the SGD solver with the backpropagation of the MLP kernels, and we have a threaded architecture where we can devote a certain number of threads to communication of the weights, and the rest are in the compute of the solver. And then another interesting part, as I just mentioned before, is this all-to-all operation, which is used for switching between data and model parallelism. So what we found, if you look at the picture on the right, like the top part is basically showing the model parallel part, where basically your colors represent different mini batches, and then for switching to the data parallel, you basically need the input from each layer, and then you need to pass the different mini batches to the different devices. So this is what was referred to as butterfly shuffle, and to the HPC folks, it should be very familiar as an all-to-all operation. DL frameworks used to lack all-to-all primitives, and the authors here actually added the all-to-all primitive in the distributed backend of PyTorch. Can we go to the next slide? So here's a platform that we actually ran this on. So the Intel Xeon Cascade Lake system with 8 sockets, and they have 3 point-to-point UPI links, and the topology is shown on the bottom left. And then for the interconnect, we use the OPA OmniPath 100 NICs, and the topology of prune fat tree with 16 nodes connected to one switch, and then the leaf switches are connected to a root switch. Can we go to the next slide? Okay, so obviously, like the paper, I encourage you to go read the paper, and the paper is actually talking about a lot of the compute and communication aspects. In the interest of time, I just took one graph to actually focus on, and this was relating with the communication overlap that I mentioned. So here we're just looking at, comparing the NPI and the oneCCL backends for 2 strategies where we were both overlapping the all reduce, and then the other one where we were doing blocking. So the chart shows that when we saw that when we were overlapping the compute, essentially it was kind of interesting to actually see that is that the compute part was actually higher for the NPI backend than it was for the CCL backend. And on further investigation, what we found out was that the like the backend thread from PyTorch was basically interfering with the compute process on the CPU cores, and essentially what our CCL implementation had was to separate out the affinity for the compute and the communication threads, so we could just move the communication threads to another set of cores that allowed the compute threads to have more better access to underlying resources and so on. So the compute actually reduced quite a bit if you look at the overlapping part. Then of course, if you go to the blocking part, then you see a very similar performance, which shows that at a fundamental level, the algorithms are just as efficient, either if it's in oneCCL or in MPI back and so on. Can we go to the next slide? So I'd just like to conclude here is that as I've described, the oneCCL is providing an interface which is really intending to match up to the training workload requirements. This allows all the system and platform level optimizations to be done underneath this API. And I think that there's already some existence proofs that it's easy to integrate into these different kind of frameworks without requiring complex workarounds, such as ordering in the middlewares and so on. And it provides one unified interface that can go over either over MPI, OFI, or the level 0 backend for the scale-up communication. Right now it essentially uses OFI for running on any hardware that is supported by OFI, and the level 0 interface from the oneAPI is expected to cover a range of accelerators such as GPUs, FPGAs, and so on. And I showed some results from the recent research, which shows that there is promise in the performance. And finally, I'd like to say that if you want to see the open source reference implementation, it's up on GitHub. Thank you. Any questions?
Let me see. No, I did not see any questions coming yet. Thank you, Sayantan, today for your time. Any other final questions for Sayantan before we move to the next session? All right. Thank you, Sayantan. I will let you know if we receive anything through our pressfab at openfabrics.org. I'll write you an email and connect you to the question.
Thank you.
Yeah, thank you.